Hi everyone, and welcome to the last video for this week. So I'm hoping that this video will be a little shorter than the last one. I know the last one was a little long and probably kind of boring for you to watch. So hopefully this one will be a little shorter, hopefully a little less boring. We're going to be talking about some new stuff, so maybe that will make it more interesting. But yeah, I hope you're all hanging in there. I know that, at least for me, the news about the virus has kind of gotten more and more intimidating as time has gone on. And, with the schools, the public schools all getting closed, it's just kind of a scary time. So I hope you all are doing all right. And, again, definitely reach out to me if you have any issues getting your work done or whatever's going on. Just let me know. Okay, so today we're going to start by just capping off our discussion of rank and nullity with just one kind of brief last thing that we didn't get to in the last video. And then the rest of the video, we're going to be talking about eigenvalues and eigenvectors, which are a new topic. And even though they maybe sound a little intimidating, they're actually, I think a lot of you will find working with eigenvalues and eigenvectors easier than some of the other stuff we've been doing. It's going to be a little less conceptual, a little more kind of computational, at least for now. And so eigenvalues and eigenvectors, we're going to spend a good portion of next week on them as well. So they're a very important topic. Okay. So first thing I just wanted to talk about was, like I said, kind of a leftover from last time. So this is the last bit of rank and nullity stuff. So 4.6. So I put this on your worksheet for yesterday. But it's important enough that I just want to also discuss it together. So basically, now that we have the language of rank and nullity, there are a few new things that we can add to our invertible matrix theorem. So a few new additions to the invertible matrix theorem. So basically, remember, the invertible matrix theorem starts by saying that you have an n by n matrix that is invertible. And so if it's invertible, we have all these other things that have to also be true. So if A is an invertible n by n matrix. So I'm not going to write down the things that we've had previously on this list. I'm just going to kind of add the new ones. So the first one, so we know that one part of the invertible matrix theorem that we already have is that AX equals 0 has only the trivial solution, right? That's one of the things on our list of what is on the invertible matrix theorem. So if AX equals 0 has only the trivial solution, another way of saying that with our new language is that the null space of A is equal to just the 0 vector. So this is basically saying, the null space of A is the set of all vectors that are sent to 0, or that are, when you multiply them with the matrix, you get 0. And so if the null space of A is just the 0 vector, that means that the only solution to AX equals 0 is that X equals 0. And so if the null space of A is just equal to the 0 vector, that means that the nullity of A, so remember, the nullity is the dimension of the null space, is equal to 0. So I know the first line and the second line almost look like they're the same thing, but they're technically saying something different. The first one is saying that the set of vectors that when you multiply them with A, you get 0, is just the 0 vector. And that's why I bolded it to kind of emphasize that. Whereas the second one, nullity is just a number, right? The nullity of a matrix is like 2 or 5 or 0 in this case. So in this case, 0 means the number 0. And it's because the dimension, when you have a vector space that consists of only the 0 vector, its dimension is 0 by definition. Okay, there's something else we can say. So we know that when you have an invertible n by n matrix, its columns have to span all of our n. And so another way of saying that using our new vocabulary is that the column space of A is equal to Rn. And then the last thing is, so if the column space of A is equal to Rn, well, we have a word for the dimension of the column space, right? That word is rank. And so if the column space is all of Rn, well, the dimension of Rn is n, and so that means the rank is n. So one thing you might notice is that we have this rank nullity theorem, right, which says that the rank and the nullity have to add up to the number of columns. And in this case, that works, right? So the rank of A plus the nullity of A is supposed to equal n, and it does in this case, right? Because you would have n plus 0 is equal to n. So it's kind of a special example of the rank nullity theorem. So yeah, so basically now, anytime, there's a question asked that tells you one of these four things, you can also then assume that A is invertible and all that other stuff that's on that list. Okay, so that wraps up our discussion of rank and nullity. So like I said, we're now going to move on to talking about something that, at least initially, is going to be kind of completely different. So we're back to talking about things that are maybe a little bit more concrete feeling. Oops, I'm going to use black to start with. Okay, so in your book, this is section 5.1. And we are talking about eigenvalues and eigenvectors. Okay, so when we're talking about eigenvalues and eigenvectors, we're always going to be working with square matrices. So we're going to start by looking at an example, and I'm not going to tell you yet what those two words mean, but by doing this example, I think you'll understand better what those words mean through an example versus if I just kind of tell you the definition. So if A is an n by n matrix, in general, if you multiply A with a vector in Rn, right, because it would have to be in Rn for you to multiply it. So if A is an n by n matrix, multiplying A with a vector, let's call it x, in Rn, what happens when you multiply them together, you're going to get another vector in Rn, right? Because of how the dimensions work out. If you don't believe me, test out, try an example, you'll see that whatever the size of the vector you multiply with, you'll get the same size of vector out of it. So multiplying it with a vector x in Rn will give you another vector in Rn. So you can kind of think about, like, multiplying by a matrix, think about what it does to a particular vector. So let's look at an example. So let's say that A is equal to 3, -2, 1, 0. And we're going to look at what happens when we multiply this with two different vectors. So the first vector we're going to multiply it with is -1, 1. And then the second vector we're going to try multiplying it with is 2, 1. Okay, so let's start by doing the first one. So if we multiply, actually let me write that out so you can keep track of it. So if we're multiplying A with U, that's going to be 3, -2, 1, 0 times -1, 1. So if we multiply these together, we have 3 times -1 is -3 minus another 2, so that's going to be -5 in our first entry. And then in the bottom entry, we have -1 times 1 plus 0 times 1, so that's -1. So we'll do the other one in a second, but I want to kind of get a visual on this. So we just want to graph the vector that we started with and then the one that came out from it. So we started by doing the vector that we started with here, so this is u, right? That was negative 1, 1, so that would be like this. So this is vector u. And then after multiplying it, we got the vector negative 5, negative 1. So 1, 2, 3, 4, 5. So that would be like here. So this is the vector a times u. Okay, so let's do another one, because once we have the second one, then we can kind of contrast what happens in the two examples. So if we multiply a instead with this vector v, so that's 2, 1. So in this case, we get 3 times 2 is 6, minus 2 is 4. And then the second component is 2 times 1 is 2 plus 0, so we get 2. So let's graph our second pair. So this is going to be v. We're going to just add something in here. So this was a times u. So v, we started with 2, 1, so that's like this. This is v. And then what came out of it is a times v, and that was 4, 2. So what you might notice is that the vector a times v is pointing in the same direction as the vector that we started with. So another way of writing our answer here, right, we did a matrix AV, so we multiplied the matrix A with the vector v, and we got a vector that is actually just 2 times the vector that we started with, right? So multiplying v with the matrix A was actually the same thing as scaling v by a factor of 2. So let me write that down kind of separately, because that's really important. So multiplying the vector v by A scales v by 2. And so another way of saying that is a times v is equal to 2 times v. So one thing I just want to point out, that kind of a distinction I want to make here, is that even though the matrix A scaled this particular vector by 2, it's not the same as a matrix that scales all of R2 by a factor of 2, right? Because if we look at what happened with our original vector u, that one was not scaled by 2. So there's a distinction to be made. We're not necessarily talking about matrices that apply the same linear transformation to all of R2. We're kind of just focusing on what it does to specific vectors. So when we have a situation like this where you have a matrix times a vector giving you the same thing as multiplying just a number with that vector, there's a special word for these things, which is that the vector is what's called an eigenvector of your matrix A. And then the number, what color have I not used yet? I think I've not used this one. The number is what's called an eigenvalue. So eigenvalue is the number, eigenvector is the actual vector. So I'll write this down below, but basically what we're talking about is any vector that has this property. So any vector that when you multiply it with a matrix, you get just the same thing as you would by multiplying a number with that vector. That type of vector is what's called an eigenvector. And then whatever that scaling number is, so in this case 2, that's what's called an eigenvalue. So I will write that below. So in general, and I don't know why I underlined that. I'm going to ununderline that. In general, an eigenvector of an n by n, like I said, we're always talking about n by n in this case. And why are we talking only about n by n? Because if we're talking about scaling a vector, it needs to still end up being the same number of components. And so in order to have a transformation where the thing you plug in and the thing that comes out has the same number of components, the matrix has to be square. Okay, so an eigenvector of an n by n matrix is a vector, sorry, let me add a word here, a non-zero vector. So I'll come back to that in a second, but that is important. It has to be a non-zero vector x such that multiplying your matrix A with x gives you the same thing as multiplying. So I'm using this special symbol. I'll tell you what that's called in a second. But so the letter I just wrote is a Greek letter. It's pronounced lambda. It's spelled like this. And it's just, for whatever reason, that's the conventional letter that is used in this context. So we'll be using that a lot. So non-zero vector x such that A times x is equal to lambda times x, where lambda is a scalar called an eigenvalue. Sorry, I'm really bad at doing U's and E's together, so I know it looks like it says something like valve, but it's supposed to be value, an eigenvalue of A. Okay, so let's do another example. So we're going to be kind of doing this two different ways. So one way is kind of what we just did, which is you're given the eigenvector and you have to find the corresponding eigenvalue. And that's kind of the easier way to do it. Then we'll do an example where you're given, or a couple of examples where you're given an eigenvalue and you have to figure out an eigenvector that goes with that eigenvalue. Okay, so let's do another example just of finding the eigenvalue. So now let's let A be 1, 6, 5, 2. And so we're going to find the eigenvalue lambda corresponding to the eigenvector 6, -5. So we're going to basically just multiply our matrix with the vector and see how much it gets scaled by. And if it turned out that it doesn't get scaled, it like completely just changes the vector, that would tell us that's actually not an eigenvector. But if I wrote this one down correctly, it should work out. It should be an eigenvector. So if we were to do this multiplication, we have 6 times 1 minus 5 times 6. So what is that? That's 6 minus 30. So that's -24. And then to get the second component, we have 6 times 5, so that's 30, minus 10, so that's 20. And so this vector that we have can be written as -4 times the vector that we started with, right? So that tells us that we have, exactly what we're looking for, right? So maybe let's call this vector v. So we have A times v is the same thing as -4 times v. And so that tells us that lambda, our eigenvalue, is equal to -4. So it's just this scaling factor. And so far, the way we're doing it, you have to already know what the vector is to figure out what that eigenvalue is. Okay, so now we're going to do kind of the opposite. So we're going to be given an eigenvalue, and then we're going to find corresponding eigenvectors. And what we'll see is that because of the way this is solved, it kind of just comes out naturally that for every eigenvalue, there's actually infinitely many eigenvectors. And so we're going to find a solution that's kind of infinite solutions, and we'll use that to come up with like one specific solution. Okay, so we are going to try to show or find, let's see, I think we're using the same matrix A from above. Let me just double check that. Yeah. So we're using the same matrix that we just were using. So 1, 6, 5, 2. And let's say that we know that we have an eigenvalue of 7. And we want to find the corresponding eigenvector. And let's call it x this time. So basically what we're trying to find is we're trying to find a vector x such that a times x is the same thing as 7 times x. And specifically, and this is important, we want it to be a non-trivial solution. And so the reason for that is that in order for something to be considered an eigenvector, it can't be the 0 vector. And why is that? Well, basically, it would just be kind of silly to say that 0 was an eigenvector, because of course it is, right? Anything times 0 is going to give you the 0. Like, of course, if you multiply something with the 0 vector and then you also multiply the 0 vector with a number, of course you're going to get the same answer either way. But that's not really interesting. So we're specifically looking for non-zero vectors, meaning that when we solve this, we want a non-trivial solution. Okay, so how are we going to tackle this? Basically, as it is, this isn't really like a style of equation that we've seen how to solve, but we can kind of rewrite it and turn it into something that we are very familiar with. So if we subtract the 7x to the other side, so that means we have a matrix times x minus number 7 times that vector x is equal to the 0 vector. So this next step, we're going to kind of rewrite this a clever way. So I'm going to write it out first, and this is something that you're probably going to want to just kind of internalize, but I will also show you where it comes from. So we can rewrite the left-hand side of this as A minus 7 times the identity matrix times x. And then I will go right down the corner somewhere off to the side, convince you that this is true. So let me just draw a star here. And let's go down here and see why that is. So if we look at the previous line, so the previous line is A times a vector x minus 7 times a vector x. So that means we have the matrix 1, 6, 5, 2 times the vector x1, x2 minus the number 7 times that vector x1, x2. So what does it mean to multiply a number with a vector? Well, that just means we're doing 7 times x1 and 7 times x2, right? You can kind of like distribute that 7 in there. But if you think about that, another way, or another like an equivalent thing that we could do is instead of multiplying the vector just by the number 7, you would actually get the exact same result if you were to make an identity matrix multiplied by 7 and multiply that with x1, x2. Right, so this matrix I just wrote with 7s on the diagonal, that's 7 times the identity matrix. And you're going to get the same result either way, because the 7s, the zeros are going to kind of create a situation where the 7 is just getting distributed to x1 and x2 individually. So if you're with me that the second line is the same as the one above, well, another thing we can do, and we haven't really done this too much, but we have written out the fact that you're allowed to do it before. So you can kind of like undistribute. So you can, here we could do, I'm not going to write all of it out. Let me just say it like this. So this was our matrix A, this was our vector x, and so right now we have A times x minus 7i times x. And so you can kind of you can factor out the x basically and rewrite this as A minus 7i times x. So kind of like a few steps of maybe not super obvious algebra, but like I said, this is something that you're probably going to want to just kind of internalize because this is how you will like always go through this process of finding eigenvectors. Okay, so now we have an equation that we can actually solve because we can figure out what a minus 7i is, right? So a minus 7i, maybe let me do another kind of off to the side so it doesn't get in the way. So a minus 7i, let's do that over here. Well, that means that we're taking our matrix, our original matrix was 1, 6, 5, 2, and we're subtracting 7, 0, 0, 7. And so we just subtract component-wise and we get negative 6, 6, let's see, 5, and then negative 5. So that's what we'll then put in back over here for a minus 7i. Okay, so now we have negative 6, 6, 5, negative 5 times x is equal to 0. And we know how to solve things like this, right? This is just now a homogeneous system of equations. So we can rewrite this as an augmented matrix and just solve as we normally do. And we have to hope that we get a non-trivial solution. So if you were to do this and get only the trivial solution, that would actually tell us that this value we found 7, or that we were given 7, is not actually an eigenvalue of the matrix. So we're hoping that we get a non-trivial solution. So if you reduce this, so just by, let's see, maybe multiplying the first row by negative 1 and then adding the bottom row, I think is how you can get here, but I'll just write down the reduced version. So this reduces to 1, negative 1, 0, 0, 0, 0. So that tells us that x2 is a free variable, so we can write x1 as x2, right, because x1 minus x2 is equal to 0, and then x2 is free, and so that means that our vector x, so this is where we need that parametric. You're definitely going to want to know your parametric vector form for this stuff. So we can rewrite x as just being x2 and x2. And so we can pull out the x2 and we're left with x2 times 1, 1. So what this tells us is that any vector of this form is going to be an eigenvector corresponding to the eigenvalue of 7. So basically, let's just pick an example. So we could pick x is equal to 2, 2. That would be an example that would work. Or you could do 3, 3, or negative 5, or pi, pi, whatever you want, as long as it's a multiple of the 1, 1 vector. And let's check that. So what should happen is when we multiply our original matrix, so that was 1, 6, 5, 2, what should happen is that when we multiply this with 2, 2, we should get 7 times 2, 2. So moment of truth, let's see. So 2 times 1 is 2, 6 times 2 is 12, so we get 14. And then the bottom we have 2 times 5 is 10, 2 times 2 is 4, so we get 14. And that is in fact equal to 7 times 2, 2. So we get a check mark here, that worked. And you could try it, I'd encourage you to try it with different numbers. Try it with a different multiple of 1, 1, and it will always work, which is kind of cool. I wouldn't necessarily be able to see that myself just looking at that matrix, that any vector with the same x and y is going to work in this case. All right, so basically that's like the same method that you're going to use on all of these. So I'm going to write that down, and then we're going to do one more example, which is a little trickier. It's just a bigger matrix, and we'll see the solutions are a little bit, there's a little bit more to interpret when it comes to the solutions. So in general, let me go back to black. So the general approach eigenvectors corresponding to a known eigenvalue lambda. So if you think back to what we were doing on the last page, what we ended up eventually solving was we found a non-trivial solution to our original matrix A minus that eigenvalue times the identity matrix times x is equal to 0. So let's do another example of that. So this time we're going to let A equal, so this is going to be a 3 by 3. So 4, 2, 2, negative 1, 1, negative 1, 6, 6, 8. And so we are going to find the eigenvalues, or sorry, eigenvectors corresponding to an eigenvalue of 2. So we're going to start by setting up A minus lambda I times x is equal to 0. So basically we're taking our matrix and we're subtracting, so in this case lambda is 2, so we're doing A minus 2i. And so it basically amounts to subtracting 2 from each entry on the diagonal, right? Because if you're subtracting 2 times the identity, that means you're subtracting 2 just on the diagonal. So that matrix is going to be, let's see, so 4 is going to become 2. And then 2, we subtract 2 and we get negative 1. And then we still have 6. And then we have 2, negative 1. And then, surprise, surprise, we also get 6. So you might look at this and think something's wrong, but it's actually okay. We'll take it a step further and kind of see where this goes. So, and yeah, I guess maybe like one thing to kind of think about is if you have a matrix where the columns are linearly independent, that means you're going to have only the trivial solution. So like, it's actually good, if you get columns that are linearly dependent, that tells you you're going to be able to find eigenvectors. But so if we were to write this as a augmented matrix, we would have this. Oops, 2. And this reduces to 2, negative 1, 6, 0, and then just all zeros. So in this case, we have 2 free variables, right? We know that x2 and x3 are our free variables, and then x1 can be written as, if you solve, so if you take this first row and you say 2x1 minus x2 plus 6x3 is equal to 0, you'll find that x1 is equal to, let's see, 1/2 x2 minus 3x3. And then x2 is a free variable, so that's just equal to itself, and x3 is also a free variable. So x2 and x3 can be anything, and then we know what x1 is based on those two. So writing this now in our parametric vector form, we have x1, x2, x3 is equal to 1/2 x2 minus 3x3 x2, x3. And so we can pull out those free variables. So we have x2 times 1/2 1, 0, and x3 times -3, 0, 1. So that means that any eigenvector corresponding to the eigenvalue of 2 is going to be of the form some number times this first vector plus some other number times this second vector. Or another way of saying that is that any eigenvector, and I'll write this down in a moment, but any eigenvector corresponding to 2 is in the span of these two vectors that we wrote down. One thing that you can do here, and we haven't really talked about this, but it's just kind of a way to make your answers look a little bit nicer. So if we're looking at the span of these two vectors, 1/2, 1, 0, and -3, 0, 1, you're not going to change the span if you just multiply one of the vectors by, or both the vectors, by a scalar. So if we wanted to, we could instead rewrite this as the span not of, or let me maybe even write it down both ways, just so that your notes feel complete if you're looking back at this. So we can think of this as being the span of these two vectors. But what I'm saying is that that's the same thing as the span of, if we were to take that first vector and to get rid of the fraction, just multiply every entry by 2, so 1, 2, 0. It's going to be the same span because those vectors, like if you take a vector and multiply it by a scalar, you're not really like changing what it has to contribute to the span, right? The span is all the linear combinations, so it doesn't matter whether you're adding in the first vector that we wrote or the kind of scaled up version. So what this means is that any eigenvector, like I said, or that corresponds to 2 is going to be in the span of these two vectors. So we could pick an example. So one example of an eigenvector that is in this span is just adding these two vectors together. So the vector -2, 2, 1 should work, right? Because that's what you would get by adding the two vectors in our spanning set together. You could also just do each of the vectors on their own, right? Each of those would be in that span as well, so you could try those ones. They're all going to work. Any linear combination of those two vectors is going to work in this example. So we can check that it works by taking our matrix A and multiplying it with the x that we came up with. So the matrix A that we started with was 4, -1, 6, 2, 1, 6, 2, -1, 8. So if we multiply that with -2, 2, 1, we're going to get, so our first entry we're going to have -8 minus 2, so that's -10, plus 6, so that's -4. And then we're going to have -4 plus 2, so that's -2, plus 6, so that's +4. And then finally we'll get -4 minus 2 is -6, plus 8 is or wait, did I do that right? -4, so it's -2, plus 8 is +2. Sorry, now I'm confusing myself. It was -6 plus 8. I just said it wrong. So it's -2 times 2 is -4. 2 times -1, that gives us -6. Then you add in 8 and you get +2. And so this is the same thing as 2 times the vector x that we picked. And so that confirms that it is an eigenvector of this matrix. And I would encourage you, if you especially are like a little bit dubious about everything I'm saying about like the span of this, try other vectors in the span. Try, these two vectors. Try this one, try this one, try this one. Try any combination of them, and you'll see no matter what combination of these vectors you choose, when you multiply it with the matrix, you should then get the result being 2 times that vector, which I think is pretty cool, or like kind of like almost surprising, I'd say. Okay, so that's about it for what I'm going to tell you. I did want to just briefly show you a couple of things on the online homework, just in terms of like the way that they're asking for your answer. So one thing I wanted to mention, so in this question, no, not that question. maybe it was this one. Yeah, so this one just, I mean, I think most of you would figure this out, but it tells you that it has two eigenvalues, and they call them lambda 1 and lambda 2, and then it asks you to find the two eigenvectors v1 and v2. So just, you know, v1 is like the eigenvector that goes with lambda 1 as an eigenvalue, and then v2 is the eigenvector that goes with lambda 2 as its eigenvalue. So same process we just did, but you're just doing it for two different eigenvalues. Other thing is that this one, they kind of are forcing you to write it a certain way. So they're basically asking you to come up with, like, so for example, the first one we did, we knew that like the x and y, or the first and second component had to be the same. So if that was your answer here, you would have to say like 1, 1 instead of 1, 2. So it's just kind of forcing you to give a very specific answer, because there are always going to be infinitely many choices, and it's just kind of like cornering you into one of those specific choices. Some of them just say find n eigenvectors. So this one you can do anything. So this is like the example we just did. It's not going to matter what your answer is. It kind of knows what all the possible answers are. So you can just put in any eigenvector you want based on your solutions. Same thing for that one. And then I thought there was one other one I want to mention, but maybe I'm wrong. I think maybe that's it. Yeah, I think that is it. So I will leave you there, and I'll post another worksheet today. For today, it will just be kind of basic stuff like this, like just finding eigenvalues, finding eigenvectors. And like I said, we'll get more deeply into eigenvalues and eigenvectors next week as well. So have a nice weekend. Remember that you have an online homework due Sunday evening, and I will be making some more videos starting next week. I might post them earlier over the weekend. I'm not sure yet, but just keep an eye out for those. All right, goodbye.